Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is part 2 of my commentary on Chapter 3 of Big C++ by K. Horstmann. We're going to talk about dangling else's, Boolean variables and operators, and input validation as an application of if-else statements. But first, we're going to talk real quickly about test cases. When you're running a program and you're trying to validate that the program works correctly, it can be hard to figure out all the things you need to test. You cannot practically try out all possible outputs. So what you need to do is come up with test cases. So for the example of the tax bracket program that we worked out at the end of the last video, you might use some test cases like this. One that's in the 10% bracket, single, one that's in the 25% bracket, single, one that's in the 10% bracket, married, one that's in the 25% bracket, married, one that's single and exactly on the boundary to make sure that it works out exactly the way it should, and you should probably then also have one for the married case that's exactly on the boundary, the 64,000. Okay, back to content. There's a problem that arises in some languages like C++ where your else does not always line up with the if that it's going with, or it's not always easy to tell which else goes with what if. If you imagine, for example, we say we're trying to calculate shipping charges for a package. The shipping charge starts out at $5 because we assume that we're inside the continental US. Then we say if the country is USA, and then if the state is Hawaii, then we can say the shipping charge is $10. We want to say else, meaning else the country isn't USA, shipping charge is $20. But that else, it's not clear which if that else belongs to. In fact, as far as the C++ compiler is concerned, it goes with the state equals Hawaii if, not the country equals USA if. So what we're going to end up doing with this is saying that in the country USA, if the state is Hawaii, will ship for $10. Anywhere else in the country will ship for $20, which is not what we wanted to do. The fix for this is to always use your braces to indicate which ifs and elses are nested inside other ifs and elses. So by putting an if but no else inside these curly braces, we force the compiler to treat the else as belonging to the country equals USA, and that's, of course, what we wanted in this case. Okay, there was a fellow back in the early part of the last century who was named George Boole, who came up with an algebra for true-false values. And that algebra is known as Boolean algebra after George Boole. To honor him, almost every programming language that allows true-false variables calls them Boolean variables. In C++, that is abbreviated BOOL, and a variable of type bool can hold exactly two values, false or true. They are not strings. They don't hold the word false or the word true. And they are not integers. They are variables that hold exactly two values, a 0 or a 1. 0 is false, 1 is true. Note that when you assign a value to a bool, when you cast something that isn't a 0 or a 1, 0 is false, and any non-zero value will be treated as true. Now here's one possible use of a Boolean variable. You might ask, why would I need to store true-false values? Well, let's say we have a process that we're about to go through on our computer, and we want to start by flagging failed as false. Okay, we're going to assume that our project is going to succeed here. Then some processing happens and something along the way happens that might set failed to true. Okay, then we might fail to be able to write a file to the hard drive, for example, or we might be able to we might fail to get access to a protected part of the operating system or something. We can then use our failed variable to make a decision later. If failed, then we handle the failure situation. Maybe we print an error code, or maybe we do some sort of backup. If we failed to write to a file on the hard drive, maybe we prompt the user to choose a different file to write to the hard drive, or a different place to write the file. Okay, those are Boolean variables. There are also Boolean operators. When you make complicated decisions, you often need to combine Boolean values. Okay, an operator that combines Boolean conditions is called a Boolean operator. Okay, Boolean operators take one or two Boolean values and combine them. The operator ampersand, which is called and, yields a true value when both conditions are, the condition on either side of it is true. So if temp greater than 0 and temp less than 100, we'll print that the water at that temperature is liquid. If both the left-hand side and the right-hand side are true, then the whole thing is true. In any other case, if either side is false, then the whole thing is false. The vertical bar operator, which is called OR, yields the result true if at least one of the conditions is true. Okay, so if temp less than or equal to 0 or temp greater than or equal to 100, we can see out not liquid. Now, how do we know to use an OR and not an AND? Well, you can tell that a temperature cannot be less than 0 and greater than 100. So that's a situation where OR is clearly the more appropriate situation. Now, if either case is true, if temp is less than 0 or temp is greater than 100, we're going to print not liquid. The only way that not liquid won't appear is if both of them are false, if temp is, say, 25, in which case it's not less than 0 and it's not greater than 100. Sometimes you need to invert a condition with the logical not operator. The exclamation point takes a single condition and flips it. Okay, if not frozen, then see out not frozen. Okay, anytime you give a not value to a truth value, you're going to get the opposite. So not false is true, not true is false. Take a screenshot of this page here on our little slideshow. This is a set of truth tables that tells you exactly how and, or, and not work. If you have two trues, you get a true either way. If you have two falses, you get a false either way. But it's the other cases, true and false is false, false and true is false, but true or false is true, false or true is true. Here are some examples. 0 less than 200 and 200 less than 100 is false because 200 can't be less than 100, and both sides need to be true. 0 less than 200 or 200 less than 100 is true because only one condition needs to be true with an OR. Okay, 0 less than 200 or 100 less than 200 is true. Okay, OR is not an either or, it's not an exclusive OR. If both conditions are true, OR is still true. 0 0 less than x and x less than 100 or x equals -1 is interpreted as if there were parentheses around the ampersand operator that has a higher precedence. So we're going to say if x is between 0 and 100 or x is -1. Okay. Consider the expression 0 less than or equal to temp less than or equal to 100. That looks just like we'd write it in mathematics, which is of course why it's wrong. It will compile okay, but what you'll get is 0 less than or equal to temp will be evaluated first. That's a Boolean, so it's either 0 or 1, and 0 or 1 are both less than or equal to 100, so that statement will always be true. Do not use that syntax in C++. You have to use the ampersand operator to break it into two different comparisons, 0 less than equal to temp and temp less than or equal to 100. Another common error along the same lines is for people to say if x and y are greater than 0. I don't know any programming language that works in. Maybe Python. Python's weird. You have to break it up again into x greater than 0 and y greater than 0. Horstmann apparently hates the American tax code, so we're getting examples of how taxes are an example of having to interpret lists of conditions. Consider these instructions for filing a tax return. You are of single filing status if any one of the following is true. You were never married, you were legally separated or divorced, you were widowed. Now, the key here is any one of the following. Okay, if it's true, if any one of the situations is true, then you need to link them with the OR operator. What about this? You are married filing jointly if all 5 of the following conditions are true. Well, if all 5 have to be true, then we need to join them with an AND symbol. When does an expression become true or false? If we have expression 1 and expression 2 and expression 3 and so forth and so on, with a chain of ands, we stop testing after finding the first false, because as soon as it's false, the entire expression is false, and we can stop there. With ORs, it's the opposite. We stop testing after finding the first true, because as long as one thing is true, the whole expression is true. The fact that we don't test the entire line of reasoning every time is called short circuit evaluation. And it comes in handy because you can do things like say, if y does not equal 0 and x over y less than 1, well, that prevents y equals 0 from ever getting to the second part of the test where you would have a divide by 0 condition and your program would hang up. Okay. Finally, De Morgan's law has to do with how we can change, we can kind of multiply nots through a series of things. So if not, country equals USA and state does not equal Alaska and state does not equal Hawaii. Okay, that's confusing. If we multiply the not through this, we get country not equal USA, or state equals Alaska, or state equals Hawaii. Okay, notice that the ands flip to ors when you multiply them by a not symbol. So not A and B is the same as not A or not B. Not A or B is the same as not A and not B. Okay. Completely independent of De Morgan's law, we can simplify some of these situations that come up commonly. In less than 5 or n equals 5, just write that as n less equal 5. in less equal 5 and in not equal 5? Well, that's the opposite. We can write that as in less than 5. In less equal 5 and in greater equal 5? Well, you can't be less than and greater than, so the only situation that fits that is in equals 5. In less equal 5 or in greater than equal to 5? Well, it's got to be one of the two, so this is just true. Not in less than or equal to 5, well, we multiply the not through, and we get in greater than 5. Not B, two nots cancel each other out, and you just have B. B equals true. If B is a Boolean, that's just the same as saying B. You can just say if B. You don't have to say if B equals true. B equals false. That's the same as saying not B. Again, you can just say if not B instead of saying if B equals false. Okay. Finally, an application of if-else's is input validation. Let's say that you actually have a little keypad that you can type numbers into instead of a board of buttons to push in the elevator. And so you could type 13, or you could type a 0 or a negative number or a number greater than the number of floors that the building has. Or you could even type a value that's not a sequence of digits, like write out the word 5. In all of these cases, we want the program to give an error message and exit cleanly instead of just crashing. To guard against an input of 13, it's pretty simple. We say if floor double equals 13, then we print an error message and return 1. If floor less than equal to 0 or floor greater than 20, again, we print an error message and return 1. The return 1 statement just immediately exits the main function, which means it exits the program. And because of the way computers used to work a long time ago, the operating system would expect your program to return a 0 if everything went right, and a non-zero value if an error was occurred. There would even be a list of predefined error messages that the operating system recognized that you could return when you were done with your program. But what if the user doesn't type a number at all? Okay, if they type FOUR, CN cannot find an integer in FOUR to assign to floor, so it doesn't set a value for floor, and instead it sets itself to a failed state. And the way you test for that is you call if cn.fail. This is another one of those member functions that we talked about with the string variable last time. With string type variables, you can call .length or .substring. Well, with cn, you can call .fail and find out whether the last time you tried to input a number, it didn't work. So we can say if cn.fail, cout, error not an integer, return 1. Okay, and that brings us to our other programming break for this week. You're going to implement the following algorithm in C++ code using Boolean variables and operators. So you're going to have a Boolean variable that stores the value for student is the right age if they're 16 or 17. You're going to have a Boolean variable that stores whether the student has passed their written test if their score was greater than or equal to 80. So we're going to have the student input their age and input their test score. And then you're going to have a Boolean variable that says whether the student can sign up for the driving test. So maybe test allowed or something. If right age and passed written test. Okay. Then if they're clear to sign up for the driving test, you're going to print eligible for driving test. If not, you're going to print not eligible for driving test. Okay. Shouldn't be too hard. And I will probably post a little bit of starter code for this that shows you how you can read in the student's age and test score. And then you just have to do the Boolean work. All right. Look forward to seeing what you come up with. Until later, good luck and happy programming.